All right, another example of convection currents that give rise to weather systems is what's sometimes referred to as orographic lift. And so an orographic lift, let's say that you have a high pressure air mass, which is, as we saw before, warm, moist, and instead of hitting a low pressure region, let's say that it's forced up into the air by a mountain. So this might be, for example, the Pacific Ocean here. And then this might be the Sierras. And then out here, this might be Death Valley. Now we know that Death Valley doesn't get much rain, but let's see if we can understand why the Sierras might get a pretty good snowpack, but we don't have much rain left over for the region of the Death Valley. So our high pressure air moves along, and let's assume that it's being carried inland, and so it starts to rise and expand again. Just like before in the last example, except that now it rises due to a topographic rise rather than being due to a difference in density between a low pressure air mass that undercuts it and the high pressure air which then rises up. So it's forced to go up over the top. It expands, cools, and then we get rain. And so if this happens fast enough, then you dump all the rain before you get to Death Valley. And these kinds of Sierra storms do tend to happen very rapidly. Once I was up at about 7,200 feet in the Sierras, upper Yosemite, and I saw this little tiny cloud, and it looked harmless enough. But then, a couple of minutes later, I looked at it again, and it looked like it was expanding like a monster. It was taking up more and more space in the sky. And then I felt the temperature drop a little bit, and I knew that was kind of a bad sign, because if the temperature is dropping, then that means that any moist air which is in the which might be in these clouds would then be subjected to condensation and then rain. And so we had left all our stuff open, our sleeping bags, didn't have anything covered with plastic, and so about half the sky was filled with this thing now, this big, dark-looking, huge cloud. So we're running as fast as we can back to our stuff, and it starts pouring rain. And we get back to our stuff and go, well, we were soaked. All of our stuff was completely soaked. But in that amount of time, it had already dropped all of its rain, the cloud had dissipated, and the sun was out again. And so fortunately, because we were at 7,200 feet, everything evaporates faster. Remember that we said before that water boils at 212. Well, it boils at much lower temperature at higher elevation. And so all of our stuff was dry in a couple of hours. And if it were down at sea level, it would have taken quite a bit longer, maybe overnight, or maybe into the next day, where the sleeping bags would have dried out. We'd had to start a fire to try to dry them out. And so that's an example then of what happens when we have a very rapidly moving storm front that moves over a topographic rise. And sometimes that's called orographic lift. That is associated with convection currents again. And so we'll come back to some of these things as we get into other subjects that relate to them. But as an example of convection, I thought that these would be two good points to bring up. And then finally, the third type of heat transfer. Remember, we're on heat transfer here. Number 3 is radiation. So in radiation then, we have essentially heat is transferred by means of electromagnetic waves. And so typically this could come from the sun, but it doesn't have to. This could come from any object that's at a certain temperature. And so we have different types of electromagnetic waves. We can look up at the data projector for a moment. These electromagnetic waves, in summary, we have AM radio waves. They have a very long wavelength associated with them, where the wavelength is just the distance between the peaks of the adjacent waves. We have then FM and television waves. Those are more on the order of maybe megahertz, 10 to the 6 hertz. We have microwaves. That's on the order maybe of about 1 billion cycles per second. We have infrared radiation, and so that is at an even higher energy and a shorter wavelength. Then we have visible light, ultraviolet, and X-rays. So these are all forms of electromagnetic waves, and they all move at the speed of light. Even though we think of visible light as moving at the speed of light, all of the rest of these electromagnetic waves also move at the speed of light. And we can say then that the sun produces all of these. But the sun tends to produce more energy in the visible part of the spectrum. And so if we were to plot this up in terms of how much energy the sun puts out in different wavelengths, what we find is that it looks something like this. This is the amount of energy per unit time, per unit area. Sometimes we call this the intensity, versus the temperature. And it follows what we call a black body radiation curve. Now it goes up a little steeper on this side and drops off a little more gently. But this is the way in which the energy can be thought of as being a, actually here, let's put here wavelength instead of temperature. This is the wavelength of the electromagnetic waves. And so, interestingly enough, in here we have visible light. So notice that we have the most energy from the electromagnetic wave in the visible part of the spectrum for the sun. But then at shorter wavelengths, here we would have UV light. So you get a fairly good dose of ultraviolet radiation coming from the sun, but not as much as for visible. Then over on this side, at longer wavelengths, you have infrared. Okay, so this is ultraviolet. This is what gives you sunburn. Over here you have infrared, so this is what gives you your heat. And then you go out to longer wavelengths here. This is microwave. And then here we have radio. Here we have ultraviolet. We have X-ray. And then at even higher energies and shorter wavelengths, we have gamma rays. So the sun puts out all of these different forms of radiation, but in different amounts. And fortunately for us, it's not peaked over here in gamma ray. Otherwise, we would be blasted by incredible amounts of radiation and our DNA molecules would be torn to shreds. Okay? But the fact that the energy is mostly in the visible allows us to adapt our eyes to see in the visible without the sensory mechanisms ionizing. And so we get above visible and it starts to ionize. So ultraviolet is where you get the sunburn. That's where you get electrons being torn off of your atoms, reacting with oxygen. And so that's not good. All of this kind of radiation from here up is harmful to the body. But all of this radiation on down is pretty much harmless. And I'm not saying that cell phone radiation is completely harmless, but it's not ionizing radiation. And so that's the key difference. And so this is the kind of energy then that the sun puts out. But as that energy comes in from the sun to the earth, it changes form. We can think of this energy as being made out of little photons. And here's the earth. So these higher energy visible photons come in, and when they hit the surface of the earth, they're turned to infrared. So in other words, the earth absorbs the radiation, and then the earth radiates in infrared. So the earth is doing a similar kind of thing to what the sun is doing, but in a much longer wavelength, lower energy rate. So this infrared comes out like this, and we reach what's called a equilibrium between the amount of energy that's coming in and hitting the earth and the amount that leaves it. But the energy that comes in is in the form of visible and a lot of these other higher energies. And what we radiate is heat energy. So the earth heats up and radiates heat that it absorbs visible from the sun, mostly. So it's this process then of the earth converting the visible light into infrared that helps to drive our weather patterns. And so the amount of energy that comes in from the sun has to equal the amount that goes out from the earth. If it doesn't, then the earth would continue to heat up. It would just get hotter and hotter and hotter. So there must be a thermal equilibrium between the amount of energy that is coming from the sun to hit the earth and the amount of energy that leaves the earth. But it changes the energy of these, what we call photons. And so the Earth's black body, this is called a black body radiation curve for the sun. And so here the temperature is around 11,000 degrees Fahrenheit. So that's what the black body radiation curve looks like for the sun at that temperature. But for the Earth, our black body radiation curve peaks out in the infrared. So this is the Earth's radiation curve. So this is at a much lower temperature. Typical temperature here might be the average temperature of the Earth, maybe, not sure what that is, maybe 50 degrees Fahrenheit or something. And, when we look at the amount of energy that's coming in from the sun, we say that, well, the Earth still radiates that same amount of energy that's being absorbed from the sun, but it does it in smaller increments. And so you have, think of this in terms of higher energy photons coming in, and then those photons break up into a lot more lower energy photons and gives rise to the heat which is radiated by the Earth.